Hello everyone, it's Professor Fiore back once again. Today's topic, Introduction to Pulse Width Modulation. What's the deal with PWM? Well, essentially, like any form of modulation, this is a way of encoding information. In this case, the information is encoded into the width, or relative width, might be a better way of describing it, of a series of digital pulses. Now, what this means is, in the normal way of thinking of it, you would have a constant frequency of pulses, whatever that frequency might be, and then you vary the width of the pulses in accordance with the signal. In other words, as the signal goes up, typically the pulse width would also increase. When the signal goes down, in other words, the information signal goes down, then the pulses would get narrower. So you can think of this as sort of dynamically changing the duty cycle of a square wave or a rectangular pulse train. So that's the basic way. But technically, you could also do this by keeping the pulse width constant and then varying the frequency, right? If you increase the frequency but left the pulse width the same, then effectively that pulse out of one cycle is getting fatter. Okay, so you can do it either way. Typically, we do it the first way. In other words, we keep the frequency constant and then we adjust the width. But either way technically is possible. We are actually going to look at the former way in this video. In other words, we're going to keep the frequency constant and literally change the width of the pulses. Now, these pulses can either be unipolar or bipolar. So if they're unipolar, the pulses are going from 0 to some other voltage. Typically, it would be a positive voltage, but it could be a negative voltage. So it's a 0 swing up or a 0 swing down. Okay, so you only have one polarity of pulse. So if you were thinking of TTL, for example, right, you'd be swinging between like 0 and 5 volts, right, plus 5. In a bipolar situation, the pulses are swinging between positive and negatives. So maybe it swings up to 10 volts and it swings down to 10 volts, negative, right? Plus 10, minus 10. So in other words, a 20 volt total potential swing. There is a special case in here that I'm going to talk about toward the end, which is called a return to zero pulse. This is a special case, all right? In any case, in any instance, what are some applications? Well, the unipolar type would typically be used with maybe controlling motor speed, or the intensity of a light, like an LED, for example. Power supply regulation is another possibility. The bipolar type is ordinarily associated with Class D audio amplifiers. And I'm going to look at a simple circuit here to basically do that, to generate that kind of waveform. So first, let's take a look at some wave shapes. So this would be a typical unipolar output. So this sort of maroon wave here, this nice big curve, this would be the intelligence signal that we're trying to encode. And then the green over here would be the pulse width modulated output. So what you find is that when the signal is relatively low in amplitude, like down here, the pulses are very thin, they're very skinny. And when the signal is pretty high, we get very fat pulses, right? Obviously, the pulse can't go to more than 100%. So that, it can top out, and obviously it can't go below 0. There's nothing like an inside-out pulse. So in the unipolar case, this is what you would get. Your signal would be coming up like this. Your pulses would be getting fatter, and as it goes back down, you can see that they're getting narrower and narrower. In this particular case, for no really good reason, the voltage of the pulse is going from 0 up to some positive value, maybe around 13 volts or something like that. All right, so that's your basic unipolar output. Now a little bit different, we have a bipolar output. So I've used a sine wave for my intelligence signal, right, the thing we're encoding. So here's this, again, maroon, nice smooth sine wave. And the green, once again, is the pulse train. The important thing here is this thing is switching from a positive voltage down to a negative voltage. It's switching back and forth. So in fact, at 0, right at the 0 level, when you look at the pulses, instead of being no pulses or really skinny pulses like it was back here, right? When When the level was really small, we had real skinny pulses. Over here, that indicates the 50% point. All right, so, right around here where you're crossing 0, right, there's your 0 volts, you look at these pulses and it's pretty much like a square wave. And then as it goes positive, we get big fat pulses, and as it goes negative, we get really skinny pulses. Or the other way of thinking about it, because we're switching from 0, is that you get big fat negative pulses over here. So wherever the signal is big, you get big pulse, right? When it's positive big, you get big positive pulses. When it's negative big, right, big negative magnitude, you get big fat negative pulses. However you want to look at it, but it's swinging, right, that full length. Now, in some applications, like you might have maybe like a bridged Class D amplifier, depending on how it's being driven, the output devices are being driven, there might be a modification on this. And that's called a return to 0 pulse. Instead of doing the full swing, you get sort of kind of like two different versions. You get like a positive version and a negative version, where it's kind of like a cross between this and the unipolar. All right, so keep this in mind. And now we go to the bipolar output. It is going to swing plus and minus, but it's not going to do the full swing on any given polarity. All right, so here's my sine wave. Notice what's happening. All right, so again, for positive pulse, as it grows, we get big fat pulses over here, right? Big pulse width. When it's small, they're very narrow, but they return to 0. They don't go to the negative extreme, right? So you only have positive pulses when you have a positive input. And then the exact opposite, the mirror image. When we have a negative input, we only get negative pulses, right? So these pulses only return to 0 instead of going all the way back up to the positive maximum, right? But it's still the same thing. Big negative, big fat negative pulses. Sometimes, depending on how we drive the output devices, the transistors and so forth, this might be a more practical approach than this, right? It all depends on how you drive the transistors, because it might be that, over here, like a big negative voltage, that might be damaging to the final output devices. So we create something like this instead, right? But still, the important thing is big signal, big fat pulse, small signal, right? You get a really skinny pulse. Okay? Okay, so what about a circuit that actually does this? Well, the simplest way of doing this just uses an op-amp comparator, right? I'm just using a vanilla op-amp here instead of a comparator, a proper comparator, just because it's easy. You can set this up in the lab and you can see it for yourself. So we have our input signal, which in this case I have a sine wave. This is an 8-volt peak sine wave running at 100 hertz. And then we have this other signal. This is actually the comparison signal, the reference signal, right? So if you've looked at basic comparator operation, right, we would call this the input signal and this the reference signal. So instead of having a DC reference, we have this variable triangle wave, right? In this case, it happens to be 10 volts peak, 10 kilohertz. Now, here's what happens. If you remember your comparator operation, whenever the plus input, the non-inverting input, is more positive than the minus, the inverting input, we see a positive maximum, in other words, a clip at the output. Any other time, we see the exact opposite. We see negative clip. So we're going to have a very dynamic situation here. This triangle wave is many, many times higher than the input signal. And this is a requirement. For this kind of circuit, this is a requirement. So let's take a look. We're going to do a transient analysis over here and sees what we get. Okay, so this is a little busy looking. Let me bring this over here just a little bit. And the first thing I'm going to do is just separate out the curves so we can see what's what. All right. So here's our signal. This is the sine wave we were talking about. And here's the triangle wave. All right. So that's these two. And then this is the output. And if you look closely, you can see that this is in fact pulse width modulated. This is that number 2 version I was talking about. Okay. The bipolar kind of output. Now, to see this a little bit better, now that we have some idea, what we're going to do is we're going to zoom in on this. Okay, and I'm going to come in here and I'm going to change the scale on here so that we can see this a little better. Make that -20. Make that plain old 20. Oops, got an extra minus sign in there. All right. So when we look at this, maybe this is a little bit more obvious what's going on here. Okay. Actually, you know, I think we could probably zoom in a little bit more than this. But before I do that, as a matter of fact, I got another idea. So here's our legend, and just to make this a little bit easier, I'm going to change the color. This is our signal, right? VSig, this is the input. So let's make this like a really different color, like maybe blue. Okay, oh, that looks so much better. All right, now compare the blue and this triangle wave green, okay? So whenever the blue is more positive than the green, right, because the blue is this one, the VSig, on the non-inverting input, and the green is the triangle wave on the inverting input, whenever this is more positive, we get a positive pulse. And otherwise, right, over here, it's less than the triangle wave, so we get a negative pulse. Okay? Of course, the sine wave is varying in amplitude. All right? You can see it's going up. Right? So the amplitude's going up. Now, look how fat these pulses are. Because this blue, this sine wave, this input signal, is higher than the triangle wave most of the time. Right? Now, if you notice there's a little gap over here, that's the slew rate of the op amp that's coming into play here. Right? There's a little bit of a delay because of that. But really right there is where, you know, if you drew a straight line right up, you'd hit there. That's right where it's flipping over. And if we continue this, right, you can see we're dropping and the pulse is getting a little bit thinner. We continue to drop. Okay, and now it's actually starting to flip. The input signals is getting closer towards the negative value, so we're starting to see fatter negative pulses. And now you're seeing, you know, really skinny positive pulses and really fat negative pulses. Okay. All right. So, you know, maybe what we'll do is we'll sort of, I'm going to zoom in here again, reset this. Tell you what, let's round the axis scale. There we go. That's a little easier. Let's do another zoom so we can see several cycles. All right. So now if you sort of scroll through this, maybe you can see this a little bit better. All right. See the way it's interacting. The input signal and the triangle wave are sort of interacting to produce this series of pulses. Okay. Okay. So far, so good. Now here's the interesting thing. At least to me, this is the interesting thing. And, you know, I think a lot of people see this and they go, well, okay, it's interesting. What goes beyond that? I mean, is it just sort of an oddity to look at? Oh, of course not. There's, you know, practical applications to this. So if you were to, right, send this pulse train off to, let's say, a little transistor that was switching let's say an LED in line, or a little bipolar transistor kind of thing, what would end up happening is when these pulses are nice and fat, you're getting a lot of current through the LED, and the LED is going to be bright. And then when it gets skinny pulses, you're not getting a lot of current, right? When you average it out. If this switching speed is faster than the human sort of visual processing that we have, which really, once you get down into like the single digit millisecond range, that's what happens. What ends up happening is you're going to see the light right? The LED get brighter and dimmer, brighter and dimmer. It's going to be bright in this area, and it's going to be dim in this area. If it was a motor, it'd be running faster here, and it'd be running slower here. All right? Now, in the audio case, right, our whole point is to, again, talking about a Class D amplifier, we're trying to reproduce this, right? We're trying to reproduce, this is the input signal, right? I'm trying to reproduce this sine wave. And this is what we have coming out. Well, you can't feed this signal as it is directly into a loudspeaker. You're going to get a whole bunch of garbage, right? But mathematically, the sine wave is in here. Well, it's in here along with a whole bunch of other harmonics, just like when you take apart a square wave, just a plain ordinary 50% duty cycle square wave, it's a whole series of odd harmonics at a very specific ratio of amplitudes, right? You put in 1 kilohertz, you get the 1 kilohertz out, but you also get, that's the fundamental, you also get some 3 kilohertz, some 5, some 7, right? And so on, right? Just keeps on going forever. That makes up the signal. Well, if you did a spectral analysis of this, right, this V out, what you would find is the sine wave is in there, right? Your original sine wave is in there, but it's sort of occluded when you look at it because there's all these other harmonics, right? Just like when you look at a square wave, the fundamental sine wave is in there, but it's all squared off. It doesn't look like a sine wave because of all the harmonics. So, having said that, can we prove this? Well, we can prove it mathematically, but, it's nice to just come up with a circuit and actually see it, okay? So what I'm going to do is I'm going to take this same circuit and I'm going to stick on the output a little filter, right? Very simple little filter, little RC lag networks. I got 2 lag networks over here, and I've set them so that they're critical at about 160 hertz each. The end result is we're going to have a critical frequency a little over, somewhere in the vicinity of 100 and, 110 or something like that hertz. And our input signal is only 100 hertz. So essentially what this is going to do, it's going to filter out all those harmonics. And we'll get back, we should anyway, get back our original sine wave. Now I've set these up, right? This is not like a really fancy filter by any stretch of the imagination, right? Here's a very basic, if you take 10K and 100 nanofarads and you figure out, 1 over 2 pi RC, you get 159 hertz out of it. And then what I did is I just added another one right after it, and I just increased the resistance by a factor of 10, dropping the cap by a factor of 10, so that this doesn't load this, right? If I had 2 identical ones, there would be an interaction and, wouldn't work quite as predictably. So that's just a little trick here, okay? Now, if you want to do this for real, you'd have a really nice higher order filter. You could control this pretty well. So in this case, pretty much, we should get a pretty nice, reclaimed or reconstructed, as we would say, input signal of this 100 hertz sine wave. All right. Now, there is a little twist here, which you'll see in just a sec. So I'm going to do another transient analysis. Boom. Okay. Let's get our legend out here. So the 2 sine waves, right? So the blue sine wave, right? This one right here, that's the signal. And then we have this red sine wave, okay? That's V lag. That's the output of this, okay? And then, of course, we have our V out, okay, which is the pulse train here in the middle. So we certainly do have a sine wave out of here, but you notice that it's not perfectly in sync. Why would that be the case? Because lag networks produce phase shifts, right? They are called lag networks because the output lags the input. And if you look at this, clearly, this maroon curve here is lagging the input signal. So yes, the lag networks do remove the higher frequencies, but they also produce a phase shift, a lagging phase shift for that input signal, right? But you are reclaiming the signal. Beautiful, okay? Now, if you try to put in a much higher signal than this, the filter, that output reconstruction filter, the lag networks are going to attenuate that signal. And then if you put in something really complicated, in other words, if you put in like a music signal, let's say maybe someone playing a trumpet or a trombone or, something else, down around this frequency, probably need a tuba, right? For you brass players, you're not going to get down to 100 hertz with a trumpet. But in any case, there's going to be harmonics there. Are you going to get the exact same waveform? No, because in this case, the lag network here is going to filter out some of the harmonics of that, tuba solo that you're listening to. The bottom line is you have to set the triangle wave and this filter to an appropriate frequency. So in the case of an audio system, the lag network would be set to somewhere around 20 kilohertz, which would be the upper limit for human hearing for young, healthy adults. And then the triangle wave obviously would have to be several times that, maybe a factor of 10 or 25 or something like that, depending on your design. So you would have to have this, and then you would go into the loudspeaker, right? I mean, you wouldn't use literally this circuit because these resistor values are far, far too big. But you would have to have some kind of filtering network before you actually got into the loudspeaker, right? Otherwise, all those high frequencies that are coming in from the pulses, those square pulses, are going to go into the voice coil of the loudspeaker, and they're going to do nothing but create distortion and heat, which is not something you want. But the important thing is we can see that that information is, in fact, encoded in those pulses in the form of a varying width. Hence, pulse width modulation. Ta-da! Okay, great. So there's actually a lot more to pulse width modulation, the practical implementation to it. But I hope this has given you a good overview, a good idea of what's involved. And if you have any questions, put them down in the comments section. Take care, and I'll see you next time.